So I did write this midterm, but I still want to edit to make sure that it goes whatever. So it's 5 problems, in the several parts, right? And I guess so. What are the policies here? So use whatever you want as far as like internet or not. I mean, you don't have to sit in a room and do it all. Open notes, open resources, but I just want you to do it yourself. So don't work in teams. And that's basically it. If you feel like there's a problem with, like an issue with one of the problems, let me know. So just let me know and I'll look up. Okay, questions about that? Yeah. Oh, right, Friday. We'll take not this Friday, next Friday. Yeah, I'll give you like a week and a couple of days. I don't like to, I don't like exams as like too much of a thing. It's just like, something you do on the side. Okay. So last time I gave a very problematic proof of the fact that a discrete subgroup of R2 looks like one of 3 things. It's either just the identity or 0 if you want. It's Z, like integers, like isomorphic to integers along some line. Or it's an ordinary lattice if you ever thought of a lattice, which is just some kind of regular pattern of points. So where you get this. Now, in other words, this would be the picture where we have CU plus CU. So these are the 3 options for discrete subgroups of R2. Now, there is a result in Artin that it kind of falls back on a few times, which is one of the dilemmas, which you can get from this. You don't have to do it before it, but I just want to mention it. So, dilemma in Artin, write down which number. That if L is a lattice, is a discrete subgroup, we call these lattices. Although there's another notion of lattice in mathematics, which is very different. So just call it a discrete subgroup. 2. And so we have 2, maybe we'll call them U and B, we'll say W1 and W2. Are linearly independent. Well, then for finitely many, P, W1, W2 is the parallelogram. Not how it's phrased in Artin, but it's the same statement. And by W1. In other words, it's saying, okay, if I have a couple of vectors, R2, and I make this parallelogram. And then I look at the inside of this parallelogram, and I look at the intersection with the lattice. Well, these guys are in here. Some will be in there. But there's only going to be finitely many other. There's a further statement which says that any element of the lattice then can also be recognized as a sum of the linear combinations of the W's and an element that's in. I just sort of translate that parallelogram around using the W1 and W2 to cover the entire. Make sense? So that's just an omission. I want to bring it back, and now I want to return. And we're going to look at a couple of discrete subgroups of isometry. We're going to really kind of focus on one type. These are, as I said last time, these are called crystallographic groups, subgroups of isometries. This is for any dimension, not just of the plane, but for any Euclidean space. You can study these things. We're just going to look at one. Last time we ended on a proposition which said that, so recall, last time, that if G is a subgroup, a discrete subgroup, M and L translations in G. In other words, it's the set of elements of R2 such that translating by that element is an element of G. I guess I should write that in the formula. So L equals the set A, R2, translate L. Then depends the E as L to L. And this is not how I wrote it last time, but this is what it's I think that any element of G will in particular, if you look at the point group, and it said actually a little more than that, actually it said that the point group, which is the image of G under the homomorphisms of the orthogonal group, that also preserves L, which is not necessarily the same thing. But I wrote it last time. Now we want to write down a theorem. That really restricts the possible subgroups that we can, that are crystallographic groups of R2. It's called crystallographic restriction. Okay. Let's let L, theorem 6.5.12. Let's let L be a discrete subgroup of R2. And H to subgroup symmetries of L. So in other words, this is the set of orthogonal transformations of the plane that will take L to L. clear what that is? So like if I take, for example, if I just took the integers inside the real line, so someone can tell me what this h would be. So it's a subgroup of O2. So I need. So O2 are these are the linear transformations of the plane that preserve distance. The linear isometrics. I just take Z inside of the plane. There's, so Z, I'm sorry, I'm thinking of Z. I'm thinking of the plane as the complex plane, so I'm saying Z, but I should probably say what I mean by Z. So let me ask this question, make sure that everyone's on the same page. This is the Z I'm talking about. So let's take the origin, 1, 0. This sits inside of the plane. So what is the symmetry of that? What is this thing I'm talking about? What's this discrete subgroup of symmetries? Yeah.
Multiplication by 1 and -1.
1 and -1. That's it. That's all that I can do, right? It has to be linear, so it has to send this origin to itself. I mean, otherwise I could potentially translate. But I'm thinking of. So if I extended this to the square lattice, I just added this standard base to this standard basis vectors and all integer combinations. What would I get? What would I have then? A new symmetry that I didn't have before. Okay. Also want to volunteer. Well, yeah. I mean, I will agree with a couple of nodding heads I saw and say there will be a new symmetry. There will be a new thing that wasn't there before. I'm looking for this group, this H. This is this, guys. This is this. I'm asking what are the symmetries of this lattice? As long as I need to fix an origin. I can do negative. That would take this point to this point, this point to this point. Let's just switch these. But what else can I do?
I mean, you can rotate by 90 degrees. You can reflect across like x equals
Right.
y.
I can rotate and reflect. Rotate it. I can reflect across an axis. So this is actually going to be D4. That you. Everyone. But early. Fire. Okay. Well, okay. So the idea is you don't have to just have. I mean, of course, the integer square lattice. You have. You could take a hexagonal lattice. You can do all kinds of stuff. You get different H's. And so the idea is of this theorem is to really classify actually which H's you can have. That's what we're going to do. Okay, so let's say we have this subgroup group symmetries, and suppose L. Let's suppose that L is not the trivial. it's a trivial group, H is all of rotation. Okay. Then okay, every rotation in H has order 1, 2, 3, 4, or 6. B H is either Dn or Dn or n equaling 6. That's a really big simplification. We're going to have we have an infinite number of possible finite subgroups. Now we just got down to a finite set of possibilities. The proof is not hard at all. Proof is not hard. So what you do is this, let's choose a vector now. Let's call it alpha of smallest possible length. As small as possible, 0. Zero length, 0. And let's choose a coordinate system. So just for fun, so that alpha looks like this. Now, let's look at, we're looking at part A here. Let's do the rotation first. So now let's rotate it. I'm going to rotate it by theta. So here it is, rho theta. Well, this length here, this vector here, which is this difference, is in L. Right? Theta alpha minus alpha. Because this rho theta is going to be an element of H. We're choosing, so I should say that. So choose any rho theta in the point group of H. Sorry, H. I can do it really thick. Okay. So this, I mean, because rho theta is an H, H is the subgroup that of symmetries of L. So this rho theta of alpha is in L. This is in L. Alpha was chosen to be in L, so their difference, L is a group, so I can take their difference as an L. So this blue guy is in L. Now, there's a certain point where that blue line has the same length as alpha. Rho theta of alpha has the same length as alpha. It's a rotation. There's a certain there's a certain angle theta where this has the same length as alpha. What's that? When? Pi over 4. For when this length equals this length. these lengths, when I have what? All three of these lengths have the same length, are the same. Pi over 3. Pi over 3. When theta is smaller than pi over 3, we're going to have that this is small. This guy has smaller. But that's a contradiction because we chose alpha to have the smallest possible length. So that means that this angle theta must be greater than or equal to. Or pi over 3, it's also known as 2 pi. Now I write that down because we had an earlier result that all finite subgroups of O2, of SO2, but of O2, all the rotation, the orientation preserving finite subgroups of O2 are cyclic. And so we can choose this theta to be the generator of that cyclic group. And the generator of that cyclic group looks like 2 pi over n. So what we're saying is that if theta is greater than or equal to 2 pi over 6, then n must be less than or equal to 6. Now there's one case that you might be concerned with. If you look at our list, we notice that we've got 1, 2, 3, 4, 6. We're skipping 5. In that case, there's this diagram, which you can kind of, it's sort of a special case, where it says, okay, where he says, all right, if it's 5, then you can look at this sort of picture. This would be essentially, if you drew this picture, which I'm not drawing perfectly at all, but if you draw this better than I'm drawing it, replicate it roughly. So there's an angle of like 2 pi over 5 here. If you rotate twice, this is going to be the rotation squared. Alpha. This is alpha. And then the point is that what you'll get from this, it should be a parallelogram, so it should go up that. So what you'll get from this is you'll get that this length here. The point is that you can then take out, you can take, I guess what is this? This is going to be alpha plus rho squared of alpha. And then this will length smaller. Just from visual inspection, but you can prove this. That length of that vector is smaller than the length. So that would, so for the case of 5, you get a contradiction. So you can rule that case out. That makes sense. So we get this finite set of possibilities, and great. So that's part A. Part A is giving us what the possible rotations that we can have in HR, and then part B, if we want to extend this to CN or DN, well, you know, we can just say, well, we know the classification of finite groups, so this follows from earlier, I want to say earlier theorem. Namely, you can take the intersection, so take H, you intersect it with SO2, the orientation preserving lines. And we know that's going to equal CN. And so by A, this equal by A. That must be and must be C1. I don't know what C1 is. It's just identity. C2, C3. And then either you have a reflection, in which case you get the dihedral group, or you don't. And then you just have this. Okay. So this accounts. So what are the lattices that correspond to these? Well, these different numbers. We sort of saw one, maybe we saw two. But you can see that you either if you have, let me just say a couple more words. If you have L equaling Z, then you'll get, as we just saw, we'll get C2. If we have L equaling, by which I mean this is integers A, 0, say, where A is an integer. If you have this sort of, this is called Z squared, which is what you think it is, it's coordinates with both integer coefficients. And then we saw that we get this C4. Well, really dihedral. And then there's this hexagonal lattice kind of built. I think the nicest way of doing it is thinking of the complex numbers as the plane rather than thinking of it as a pair of two real numbers. And if you do it that way, you can look at the generators of sort of, you know how we said everything is generated by Z times U plus Z times V. So we can take Z times 1 plus Z times e to the 2 by I over 3. Or even pi I over 3. I don't want to do that. What it'll look like is, you have some kind of thing here, and you rotate by, pi over 3. Do it exactly. Look at this hexagonal picture. And if you guys have all been in bathrooms. Like this tiling, if you look at like a bathroom, almost 90% of bathroom floors or something, you'll see some like tiling like this. But this the vertices here form the hexagonal lattice. And it's a closed subgroup. Okay. So next section is really about these crystallographic groups, and it's sort of its own little nook, own little corner of as far as it's a topic. I wouldn't say it's essential, but it's a very pretty topic. And he looks at one example sort of in detail. So these are going to be discrete subgroups of isometrics. And in the case of that we've been dealing with, namely the plane, they're two-dimensional. The point is if you take these things will describe symmetries of these types of tilings. And of course, these tilings, there are a lot of applications for this. So if you look at certain types of images like graphite or some certain molecules that have regular patterns. These symmetry groups sort of just symmetries of these regular patterns. It can be used to simplify some of the complications. So we're studying. And the first comment he makes, which is a nice comment, and I think kind of shows up on the midterm, is that if you take a group, so let's say we have a group G, subgroup, crystallographic group, and you take its point group as the image of it under the map to O2, and you take its lattice of translations, L, that these two things, while they tell you a lot about the group, they don't determine. In other words, full. In other words, you could have cases where you have the same point group, the same group of translations, but the actual group G is different. That said, they do tell you quite a bit, and so we want to look at one example. So he gave an illustration. He has these really nice pictures of all of these different things. And one of this one here, he gives this particular illustration. And the point is so if you look at the lattice of translations, there's this reflection, which is a glide reflection in this case. Along this, there's a glide. So if you just reflect over this, it's not a symmetry, because this point would go to something that's not in this pattern. But if you reflect and then translate, you do get this reflection. And so, I mean, his point here is that you can look at this point group. You could also, and you could look at and it will contain a reflection, right? You can look at the point group and it will contain a reflection, but the actual group does not contain a reflection. It's a glide reflection. Symmetry. So what is the point group? The point group is the group that is the image of your group of isometries under the map to orthogonal. So it'll take glide reflections and send them to reflections. So if you just look at the point group, you'll see reflections in the image. There is no actual reflection in that. But you can certainly build a group with the reflection and with all the translations. That would be fine, but it's not this one. It has the same sort of two distinct groups with the same information. If that went too fast, please read through that. And I think that's it. All right, so but what he does in this section is he focuses on the case where n equals 4 from the last classification. So this is sort of a case study. N equaling 4. For symmetries of the translation. L of G. We have some discrete subgroup, some crystallographic group. We have some lattice L, that's the translation subgroup. And we're going to say, okay, what if n equals 4? What kinds of groups G do we get? Okay. The first thing to do is to look at L. Look at L. Here's a theorem. Point group of G is equal to C4 and L is C squared. Well, I should say isometric. you may need to change your coordinates slightly by rotation. Instead of points in the plane where each of the coordinates is managed. But it's really quite. Since R is equal to contains. So if it's D4, it contains D4. There is a rotation. Remember, all of the elements of O2 are either are a rotation. About some point. We can say that we can, because G fixed L, we can say that this point is. And the point is that what we did prove is that any element of N that is orientation preserving is either a translation or a rotation. About some. And so what I'm saying is, okay, well, if I look in the image of translations is identity. I go down to when I take this homomorphism to O2. So if I look at the thing that's sent to a rotation, it had to be a rotation. And it was a rotation about something. It didn't have to be a rotation about the origin, but it has to be a rotation about something. And since it preserves L, that point should be, that's maybe an exercise. So let's shift our coordinates so that this is rotating about the origin. We can do that. This point is no. We may assume. Can't always do this with reflections, but we can do this with this. So I just said this. It looks like I'm repeating myself here. I mean, by where with standard coordinates. I'm just, if you don't like that, you can say, well, let's fix our coordinates at this point. Anyway. Since the rotation about some point, we may as well assume that point is 0. So now choose, now L is equal to, by what we've proven, ZU plus EV for some vectors. But in particular, we can take U to be some vector. It's going to be it's going to be, well, it's going to be some take rho 5, 2. In other words, we can rotate U by 5. Okay, well, then W is orthogonal. And of the same length. So again, if we fix U in this direction, rotate it, here's W. These two vectors have got to be in L. I'm identifying these vectors. So we get a square in L. I mean, if we think these guys. Now, what I said at the beginning of class is that there's this lemma which says that then the number, that if I look at the square, the parallelogram, there's a finite number of elements. So there's at most a finite number of elements, but in particular, let's say there was any element in it. So if any element of L this parallelogram, which I denoted by P, U, W. Well, I should have said, I want to choose U to be of smallest length. So let's assume if U wasn't of smallest length, then V would be, you can switch it. So assume U is of smallest length. So I'm sorry, I forgot to make. So if any of these points, if any blue element is in here, so if any other element of L is in this, then its distance to one of the red points is less than the length of U. Strictly less than. And that's, you can just take these, you can just take the circles. See what that's like. But that would contradict the minimality of the length of these. So that means that there is no other element of L in this square. But as I said, any element of the lattice can be translating using U and W to some element in that square. So the only other elements of the lattice are actually just in the integral span, the integer span of U and W. In other words, W is V, or well, W is a combination of U and V. Trying to get it. And this is the square lattice. We can identify, it's isomorphic to the square lattice. So in other words, I can identify this by scaling with 1, 0, and identify this with 0. So when I say isomorphic, I guess I should be a little clear about what I mean by that. Maybe I should say L is isomorphic to this. What does that mean? Of course, everything is isomorphic as a group. Here I mean up to scale. I do need to be able to scale. Scaling the entire thing by a single number. Otherwise. Okay. Yes, please.
Does that mean that V has to be some integer multiple of this W we found?
No, it means that it's an integral combination of U and W. So I really didn't even want, I don't know what, I was talking about the theorem, and so I wrote this down. But what I should have said is I should have just said, take U to be the smallest length vector, or a smallest length vector in L. I didn't want really to, I mean, I was trying to remind us that we had this isomorphism, but that was not what I should have written. So my mistake.
Okay, because like V could be the diagonal.
Yeah. V can be a linear combination, right? V can be any sort of, V can be an infinite number of possible things. A lot of things. All right, so we get this square lattice. And then, well, so the rest of this section, which I don't think I'm going to have time to prove, and I do want to kind of move on to group actions because it's really much more important than this. But the rest of this section then explores what types of groups you can have here. So basically, in the case when n equals 4, we're sort of, I'll write down the result and I'll let you guys read the arguments. So there's basically two possibilities. I mean, and within, okay. So n equaling 4 case, we have some G is a discrete It's a crystallographic group. In M. And we split off into two possible cases. We can have that the point group is equal to C4. And if this is the case, then in fact, then G is isomorphic to just basically the set of, well, here you can take this TV. So what is rho here? Rho is just take rho equal to this rotation by pi over 2. So if you have the point group is just C4, no reflections, then this is what you do. On the other hand, if you have the point group is the dihedral group, then you have a couple of subcases up to isomorphism. The one, you could have something very much like you did with C4. You can have G is isomorphic to all of the elements that you would expect. So TV rho I, and then also TV rho I with a reflective standard R, where so this is, it's basically the same idea as this. You're just going to take the dihedral group and then you're going to add discrete translations. Or you can, and that's kind of not, that's in a sense, that's sort of boring. You can have something more interesting. And this is kind of where you see these sort of glide reflections starting to pop in. So here you have this, you will still have this point group corresponding to the orientation preserving part. So you'll always have this guy in here. Then now you don't have this kind of reflection. You have Tu rho I R. So this is going to be necessarily a glide reflection. So now U is no longer B in L. U is rather equal to B plus C, where B is in L. And what is C? C is equal to the vector 1/2, 1/2. Your L is our standard lattice. It wasn't Z squared. So this C is saying that the reflections that you have in this is sort of the interesting, I want to say this is really the interesting thing that starts appearing when you look at these classifications. You get some subgroups, crystallographic groups that really don't behave the way you would expect. And they have that property that the reflections aren't there, they're glide reflections. But how do you glide? You glide sort of not completely along the lattice, but at sort of a half rate. Diagonal. This is sort of the only possibility once you fix your square lattice. Sort of a center of your square that you glide to. So anyway, that's the result. As I said, hardly have time to write it down. So I don't have time to prove it. I do want to go on. I want to talk about group actions next time. I've made a big list of all of the applications, and well, that just came into my head. Geometry, physics, combinatorics, network theory, algebraic applications, and all sorts of other applications, analytic applications. So there's all sorts of applications of group actions. I want to say group actions are really where group theory can be applied to other areas, and the most important thing to kind of take from group theory, I'd say. So we'll spend a little time on it on Friday. And then I think we're going to move on from groups, but I will see you Friday.
Any other questions? Nine, we included problems. I think these were going on.
Okay, yeah, if you already did, so I tried to change last homework so that I wasn't assigning homework that was in the section. But I changed it sort of late. So if you had already done the problems that got moved over to this week's homework, you don't have to do it. Don't worry about it.
So I already did these. I
Yeah.
have to do them again.
Yeah, no, you don't have to do them again. I just moved them over because we couldn't really cover everything.
So I'll just submit these four.
Yeah,
and-
yeah. That's fine. Maybe write a comment on your homework that you've done the previous one.
Okay.
So that when I look at it.